So today we're going to start with Valentijn de Jong, who's here visiting us from Utrecht, and he's going to talk to us about individual patient data meta-analysis of intervention studies with time-to-event outcomes. So he's a PhD student at the moment focusing in that area. So I'll just get your slides up. Over to you.
Thank you very much for the introduction. So yes, indeed, I'll be talking to you about meta-analysis mostly. This is a project with several other people here, listed here. So I'll be talking to you first about the how we set up the review, and then I'll show you some of the important results. We'll start off with the estimation of treatment effect in RCTs, then the heterogeneity thereof, and then predictive models for predicting treatment effect in individuals. So first of all, the usage of individual patient data, so that is data on every individual in the meta-analysis, has become increasingly common. And that is simply because it is the gold standard in medical research to have the data of all the persons. This offers several advantages for the meta-analyst, as you can decide you have all the decision on how to analyze the data. And that covers many things. So there has been a lot of guidance on other IPD meta-analysis for binary continuous outcomes. You have Thomas and Higgins et al. And Hereby et al. Have covered a lot of outcomes. But for time-to-event data, they note that there was more guidance necessary. So that's why I'm talking to you about this. We have a systematic search. Not the entire review is systematic, but this is. It focuses on three aspects. First of all, individual patients. Secondly, either meta-analysis or hierarchical models. And thirdly, survival models or any other type of survival models. We found over 1,000 results in PubMed and also 1,000 in Web of Science. A lot of them were duplicates, and after removing all of the non-methodological articles, we only have 141, including suggestions. Don't worry, I'm not going to bore you with 141 articles. I'm going to talk about the ones that are relevant to our case study, which is epilepsy patients. So in 5 RCTs, the effects of carbamazepine and valproate were compared for the time to first seizure once the patients entered the trial. Here you see, this is all of the patients combined, Kaplan-Meier curves. We see for the 2 treatments the time to first seizure. A lot of them already have a seizure in the first half year, but also some of them never get a seizure anymore, at least not in the trial. And then we're interested in comparing these 2 treatments. I'm saying comparing these 2 treatments, but we have to ask ourselves which type of treatment effect we're interested in. Are we interested in a marginal treatment effect or a conditional treatment effect? In a marginal treatment effect, we're interested in the population as a whole, and we can use regular statistical analysis to estimate those, but we have to adjust for the correlated event times. And in a conditional model, we're interested in the effect of the treatment relative to other patients in the same study with the same frailty and the same covariates. So we model this dependency between patients by using frailties. Now both of these models are available in common statistical software, and really choosing between them depends only on which type of treatment effect you're interested in. In IPD meta-analysis, you're commonly interested in the study-specific estimates. We want to know why there are differences in the study-specific estimates, and we want to investigate the heterogeneity. And therefore, I present to you here the conditional models for the rest of the presentation. For the estimation of treatment effect in time-to-event models, we commonly use the Cox model. I'm wondering how many people are familiar with the Cox model. Is it everyone? Yeah? All right. So on the left-hand side, we have the baseline hazard, which we can either have a common baseline hazard, or we can estimate it per trial if we want to stratify out all the heterogeneity. On the right-hand side, we have the betas. We can estimate them per trial also, or place a random effect on it. And of course, we could have a common effect. So if we place a random effect here, it's typically called a random effects model. But we can also place a random effect on the alpha, so on an intercept, basically. And then we call it a frailty model. Although essentially in both cases we are applying a random effect. For the frailty, typically one uses a gamma frailty or a log normal frailty, or we can leave it fixed to 1 and then apply random effects to the beta only. So we have a lot of variation here. We have more options than in the analysis of other types of data. Some visualization. The red is for 5 studies, the 2-stage analysis. Over every study separately, we do an analysis. And then on the bottom, we have the mean effect in all studies. And then in blue, we have a 1-stage model. So the model I showed here with random intercepts, if I recall correctly. You see that the study-specific estimates are much closer to the mean effect as the frailty penalizes them and pulls them towards the mean effect. We can quantify this heterogeneity between the studies, so we see that there is some variation in treatment effect between the studies, although in this case the confidence intervals overlap quite a bit. But we can quantify this on a scale of the hazard scale, of the hazard ratio, using the median hazard ratio. It is related to the normal distribution or to the gamma distribution, if you prefer that one. And, that's 1 to 4. In this case, we found a hazard ratio of 1.8 for the treatment, and a median hazard ratio of 1.1 for the treatment. So they're basically on the same scale, and this means that the median relative difference in the hazard ratio for the incidence of seizure is, so for 2 identical patients from 2 randomly selected trials, is quite similar. So this is, I think, personally more intuitive than saying, well, the I-square is like 10%. Yeah. So this is also specific for time to event data. So there's a lot of sources of heterogeneity possible. For instance, differences in outcome definition or in treatment dose or in the case mix of patients. And it's commonly recommended to identify where these heterogeneity come from. So in this case, here we're looking at case mix. One variable is specifically the epilepsy type, which can be either generalized or partial onset. Here we have centered the variable of epilepsy type, even though it's 0s and 1s. And that's because we have to avoid ecological bias. This is also commonly reported in the mixed effects or hierarchical models literature, but you won't see it as much in the meta-analysis literature, even though it's necessary. So the centered variable describes the effect of epilepsy type, and the trial mean describes the effect of the ecological bias that might be present if you ignored it. There's also some sources of heterogeneity very specific to time to event data, and these are time varying effects and follow-up times. Here we see the Kaplan-Meier curves stratified by analysis. We easily see that the green and the blue lines are far longer than the others, so those trials took much longer. What's very specific for time to event data is that there are selection effects due to the frailty of the patients. As you can see, the first reference is from 1979 already, even though commonly right now, if you look at the literature in epidemiology, this is not something that's commonly discussed. I'll give you a very simple illustration. We have the control group here, and this is the risk the percentage that's still at risk. So the frail patients obviously have an event much quicker than the more fit patients. And in a medication group, those are, well, if you have a protective medication, then they won't have an event as quickly. But also there, the fit patients are survive longer than the frail patients. Now, if you look at the 1 year risk, in the control group, the frail patients have an event very quickly. They leave the population, so we're left with fit patients. Whereas in the medication group, as the medication is protective, the frail patients won't have an event as quickly, so they won't leave the population as quickly. So we see a different. We observe a different risk ratio through the time. So this is then the risk ratio between the two groups over time. Now, if we ignore this, then this would all be bias, if you're looking at conditional effects. So that's very specific to time to event data, which we should always keep in mind. We can easily investigate this, again, with common statistical software. I've plotted the 5 different trials in different colors. Through time, we see the beta for the drug, for the difference in the drugs. And the black line is the average. And we see it declining, so I'm not sure whether this was significant or not. Doesn't really matter. What we see is a different effect of drug through time, sorry. Getting to the final part of the presentation, predictive models. We can also predict the treatment effect in individuals. We can do this with the Cox model. There's just some small issues. The baseline hazard can be a bit problematic, as predictions are idiosyncratic. So the 30-day survival prediction may be very different from the 31-day survival prediction. And finally, the modeling of non-proportional houses can be a bit cumbersome. On the other hand, we can use parametric survival models. They have a smooth predicted survival curve, and they're more parsimonious. When the distribution is correct, but only then, I think, they have more precise estimates, and we have a variety of methods for non-proportional hazards. And the last one is both a good point and a bad point, because you have a lot of options, and a lot of them can be wrong. This is just 3 options. First of all, the libel model is, I think, the most common model in survival analysis. Secondly, the log logistic model, which is proportional on the cumulative odds scale, so that's also a scale that's interpretable. And thirdly, the generalized gamma model, which I think is a horrible equation, and I don't want to look at it. The libel has 2 parameters, the log logistic 3 and the generalized gamma has 4. If we apply them to this data, first we see the libel model does not fit very well. Secondly, the generalized gamma model, which has 2 more parameters, fits a lot better already. And thirdly, if we apply the log logistic model, it doesn't fit very well, but this one is fitted with splines. So that's an extra option I hadn't mentioned earlier. This one fits quite well. We cannot test the difference between these models with p-values because they're not all nested, but we can use an information criterion. Here I've used the AIC, and either the log logistic with splines or the generalized gamma fits the best. But again, I've only considered a few types of models here, and there's, I don't know, an infinite type of models. That was it. The conclusions. There's a lot in common between time to event IPD-MA and other IPD-MA, but the baseline risk really presents quite a few issues and also options. We should always expect heterogeneity, so I think we should always apply a frailty model or a random effects model, and we can predict treatment effect with a whole variety of models rather than just one. Thank you. I have a ton of references, but I'll just skip through them. Thank you.
Thank you, Valentijn. Are there any questions? Yes, at the back. Yeah.
Okay, I'm not an expert in this, so I'm not but since you have mentioned, I'm just curious, have you tried the flexible parametric model?
Yeah.
And how much difference between the flexible parametric model and your standard parametric?
So with the flexible parameter, are you referring to, for instance, the knots we are adding, or the linear, sort of non-linear term? Oh, right. Well, I think it's just a formalization of the options we have. So normally we commonly apply things, the functions linearly, or in epidemiology they like to take cutoff points. But then in the flexible parametric models they say, well, we start with linear, but we'll also try, and we will always try other terms as well. So we always try the quadratic and things to the third power, but also the square roots. And they've set up some formal rules for testing those. Whereas commonly now what people do is they just try something. They're like, oh, this might be to the power of 2 or 3. So I think it is a good option. We should be upfront about it, say from before we start to research. Well, we're going to try these options. So I think that's good. Does that answer your question? Or?
Maybe we can chat about it later after the in more detail. Are there any other questions? Yes.
Question. Thanks for the presentation. I'm envious of your generalized gamma conversions. In my limited experience with it, it's never got to converge with all parameters there, so it's great that it's working. My question is about heterogeneity. You mentioned the I-squared statistic. So you can certainly do that from the two-stage meta-analysis, the way you've done. But are you aware of doing an I-squared type statistic from a single-stage meta-analysis? I've never seen it, and I've never really understood why. I'm just wondering whether you've come across that exploration.
From what I remember, it's, for the I-square you need an accurate estimate of the tau square, which at least common statistical packages do not produce. I'm not sure whether it's just entirely impossible or whether just no method has been found yet. I think you can make estimates, but I think the packages just don't do it. I'm not sure whether those estimates would be valid.
No,
I think that's the reason.
A fundamental conceptual reason why it's never done, whether it's the within study variance is too difficult.
Yeah, I think it has to do with the estimates of the there's different uses of estimate. The default estimate of the tau square statistic is different in the one stage than in the two stage. That's what it's related to. As for the generalized gamma, I used some packages and everything went smooth. I have no idea. I didn't tweak it or anything, so it wasn't me who did.
Sorry, I came in late, but is Andrew's point about survival analysis context specifically, or?
He mentioned that he preferred this was a median hazard ratio as the sort of measure of heterogeneity opposed to some I-squared. And just triggering thinking about I-squared from single stage meta-analysis rather than two-stage.
Right.
Yeah, I think for statisticians, an I-square is nice, but because it tells you about the proportion of the variance. I think for more applied researchers, they're just thinking, yeah, well, I have no idea what this means. So that's why I think a measure that's on the scale of the estimate you're interested in is a good thing.
Okay. Any more questions? No? Then please join me in thanking Valentijn again. Yeah. And our next speaker is Dr. Jennifer Thompson. Jenny, I think I may call you. So Jenny is a trial statistician and methodologist, and her research focuses on developing statistical methods for the use of cluster randomized trials. And our talk today will be about advice for using generalized estimating equations in a step-wedge trial. So let's see if we can get up your presentation. So do you prefer the PDF or the PowerPoint?
PDF probably.
PDF? Okay. Let's see.
Control L, isn't it?
Sorry?
Control L.
Oh, Control L. That's great. Thank you for the shortcut.
Yeah. Hello, everybody. So today I'm going to be talking through some results from a simulation study I've been working on, looking at how we should be using generalized estimating equations if we're trying to analyse a step-wedge trial. So for those of you that aren't familiar with what a step-wedge trial is, it's a type of cluster randomised trial. So we randomise groups of individuals like hospital wards or classes or villages rather than individuals themselves. And in a step-wedge trial, rather than randomising whether or not a cluster will get the intervention or not, we randomise when the cluster will get the intervention. So clusters, which are the rows on the diagram here, are randomised to sequences, and each sequence switches from a control group to the intervention group at a different time during the study. So at the start of the study, all or most of the clusters are in the control condition, but by the end of the study, all or most of the clusters are in the intervention condition. So because we have control and intervention observations within the same clusters, we have different ways that we can estimate an intervention effect in these studies. So first of all, we have what are called vertical comparisons or within period comparisons. And for these, we separate the study out into each period. So we call the times between different clusters switching the periods of the study. And within each of those periods, we can compare observations in the intervention condition to observations in the control condition. So they're a bit like mini parallel trials contained within the step-wedge trial. But in addition to these, we also have what are called horizontal comparisons or within cluster comparisons. Sorry, my green's a bit too light for this slide. But for these, we compare within each cluster, we can compare observations collected during the control to observations collected during the intervention. A potential problem with these comparisons is that the intervention is collected later in time than the control, so our intervention effect is confounded with changes in the outcome over time that aren't related to the intervention effect. So we need to take that into account in the analysis. So I've mentioned two things we need to take into account: clustering, because we randomise groups of individuals, not individuals themselves, and secular trends, the changes over time, not related to the intervention. And we also need to take into account the correlations within clusters over time. So the simplest assumption we might make about how correlated observations are in different time periods, or within one cluster in different periods, is that all observations within a cluster are equally correlated to one another. And that might be a good assumption in some settings, but in other settings we might expect observations collected closer together in time are more correlated to one another than observations collected further apart in time. So this is just a little schematic of that. So we have rows and columns for each period in a study. Observations collected in the same period are a darker colour indicating a stronger correlation, and observations collected further apart in time, say period 1 with period 6, are a lighter colour indicating a weaker correlation. And this can affect how much information we can get from those within cluster comparisons. So in order to take those three things into account, there are the most commonly used methods are generalized linear mixed models. So here we use random effects to take into account those correlations and model those correlations. But there's a growing amount of research in step wedge trials that, like in other settings, generalized linear mixed models require correct specification of those correlation structures to give you unbiased standard errors. And this is quite difficult in a trial setting. You often don't have a lot of information beforehand about what underlying proportions you might expect, let alone how those might be correlated over time. So it'd be useful if we could have another method of analysis that was a bit more robust if we weren't sure what to expect of those correlations. And I'm going to be talking about generalized estimating equations, which are known to be more robust to misspecified correlation structures in other settings. So in other settings, they're known to be robust, but this hasn't been looked at for step wedge trials. Another downside of using generalized estimating equations is that they generally need a large number of clusters. And this is a problem because step wedge trials usually have, the average is 18 clusters, so not very many at all. However, there are small sample corrections that we can use to correct the problems by having a small number of clusters. But again, these haven't been looked at for step wedge trials, so I'll be looking at how well these work in this setting. So this was a simulation study where we used a binary outcome, included a really simple linear change over time to make sure we're accounting for the secular trends. I looked at a variety of different within period intracluster correlation coefficients. So that's how much within one period, how much correlation there is between observations in the same cluster compared to different clusters. And then looked at several different correlation structures within each cluster over time. So this is an example of one of the correlation structures considered in the simulation study. So it's like that first autoregressive correlation structure, but we might expect other things that happen in the study to affect the correlations. So for example, you might expect that after you've introduced the intervention effect, observations will be less correlated than they were if they were both in the same, both in the control or both in the intervention. So again, that's just illustrated here. 2 observations in the control or 2 observations in the intervention have that same autoregressive correlation structure that we looked at before. But if one's in control and one's in the intervention, you have a weaker correlation. So this would be very hard to know if it was going to happen up front to pre-specify in your analysis plan. In terms of trial designs for the simulation study, I used this schematic shown here. So it has 6 sequences. I looked at clusters ranging from, a number of clusters ranging from 6 up to 60, either 24 or 60 observations per cluster, with scenarios where all clusters were the same size or where that number varied between clusters. So for each combination of those scenarios, I generated 1,000 simulations and analysed them with several different analysis methods. So we have 6 generalised estimating equations with robust standard errors, so 3 different working correlation matrices, independent, exchangeable and autoregressive. So autoregressive is closest to the truth, but not exactly the same as the truth. And these were used with and without a small sample correction. So in this work, I've just used the Fay-Grabard small sample correction, which is one that has been shown to work well in similar settings. As a comparison, I've also included a generalized linear mixed model. So this is the most commonly used method for step wedge trials, and the most commonly one just includes a random intercept for cluster. So it assumes that all observations within the same cluster are equally correlated to one another. So we're expecting that one to perform quite poorly. All of the methods adjusted for time as a categorical variable. So starting with some results, these are some results from when we have 60 clusters in our trial. I'll be showing results from having 24 observations per cluster and that varying between cluster, but that didn't seem to affect results too much. So in this scenario, we found no effect estimate bias for the intervention effect, and that was true in all of the scenarios we looked at. But with the standard errors, it's a different story. So the red line at the bottom is the generalized linear mixed model, and you can see how standard errors are biased because it's made the wrong assumptions about the correlations within clusters.
Are they too small? Is that the direction of it?
Yeah, yeah. And the generalized estimating equations, even though we have 60 clusters, we still see some bias where the standard errors are too small. This then leads to low confidence interval coverage. But if I add in the corrected generalized estimating equations, you can see that corrects the standard error bias, and we're left with nominal confidence interval coverage. The choice of working correlation matrix doesn't seem to have made any difference at all to these results. If we reduce it down to 48 clusters, it's quite similar results. With 18 clusters, the difference gets larger, so the uncorrected generalized estimating equations are down to less than 90% coverage, but the corrected generalized estimating equations have nominal coverage. If we go as low as 6 clusters, which is surprisingly common in step wedge trials, the corrected generalized estimating equations are overcovered, which isn't great, but it's not as worrying as having undercoverage. So in that scenario I showed, the previous scenarios, the choice of working correlation matrix didn't make any real difference to the results. But there were some scenarios, more than we would have expected by chance, where the exchangeable working correlation matrix and autoregressive working correlation matrix had slight undercoverage, but using the independent working correlation matrix maintained nominal coverage. So I'm still trying to look at patterns for when this happens, but it does look like there might be some issues sometimes with the exchangeable and autoregressive working correlation matrices. And I'll just finish up by talking briefly about the power of the methods. So here you can see that it looks as though the uncorrected generalized estimating equations have much larger power than the corrected generalized estimating equations. But that's because the standard errors are biased downwards. So the main take home from this is that you need to take the small sample corrections into account when you're doing your sample size calculations at the start of the trial. Otherwise, you'll end up with an underpowered study. If we just look at the corrected generalized estimating equations, we can compare power by the choice of working correlation matrix. And there's not very much difference in this setting. So the difference increases as the ICC, the intracluster correlation coefficient, increases, but we're still only looking at a few percentage points. So it might be worth using the independent to get that increased robustness against undercoverage. So just to finish with some conclusions, we've confirmed, as has been shown in other settings and some other studies for step wedge trials, that generalized linear mixed models are very sensitive to correct specification of the correlation structures. We found that generalized estimating equations with a small sample correction are a really good choice of analysis for a step wedge trial. They're not affected by misspecification of the correlation structures, and you do need a small sample correction even if you have quite a large number of clusters, we found, but the Fay-Grabard correction worked quite well. And there's little difference between the working correlation structures. I think that's everything. Thank you very much.
Has anyone got any questions?
I don't quite have an intuition for why, on your charts against ICC, it's not monotonic. You seem to go, lots of your lines seem to like V shapes.
Yeah, I think that's random variation.
How many repetitions do you do?
1,000.
Oh, okay.
These
Quite
are-
a lot.
Yeah, it seems to be quite random whether they go up and down or...
Okay. Should there be a trend?
If anything, I would have thought it would get worse as the ICC increased. But I'm not, yeah.
I don't know.
It's an interesting point, something to look
I
into.
mean,
you kind of want a fourth point, so you can try to draw a line through 3 points.
Yeah, yeah. I'll take that into it because I'm continuing this work, so I'll make sure I look at that going forward.
That's a very interesting talk, thank you. I just wondered, I wasn't sure what I might have missed as to the actual model that you simulated from and the parameter that you were estimating. Was it a marginal odds ratio or a conditional odds ratio?
Yeah, it was a marginal odds ratio.
And so how did you get the GLMMs to estimate that? Or were they sort of corrected to?
So the generalized linear mixed model was estimating a slightly different effect, but because the ICCs are relatively low, the difference was quite small. So it didn't seem to make much difference to they still were relatively unbiased. So a little bit of a fudge, I know, but
The main issue still stands, I guess,
yeah, the standard errors would have been affected by that, I don't think.
So just again, how did you simulate the data? What was the model?
So it was simulated from a latent normal distribution, and then using the using cutoffs to create the binary variables from a multivariate normal distribution.
Where you had to sort of fiddle to get the desired odds ratios by trial and error?
So the odds ratios were converted to probabilities, and the correlation structures I wanted were used to create the multivariate normal distribution. Yeah. I think this work, the correlations that I've shown here are the correlations used for the normal distribution. You can, through trial and error, change them to be on the probability scale, and it gets a little bit more complicated doing that.
I think in the interest of time, we'll move on to Simon's presentation, but hopefully we can take this up
Yeah,
further
happy to discuss
if
this.
we're able to make it. Thanks very much. Okay, our final speaker is Simon White. He's visiting us from the Medical Research Council Biostatistics unit in Cambridge. And I'm trying to remember what you're talking about, sorry. Neuroimaging today. So Simon has very varied interests. Does some Bayesian work, he does some stuff fixing cohorts, and today he's going to talk to us about modelling heterogeneity in neuroimaging people and the brain. Sorry, that was a really terrible introduction. Over to you.
So I thought I'd basically give a little run through of my story through neuroimaging, and basically how sometimes it makes me cry inside what they actually do in some of their fields, and some of the work I've tried to do to think about introducing one of my main research interests, which is heterogeneity. I couldn't do this talk or any of the work I do without a large number of people. Does my pointer work? Oh, it does. No, it doesn't really. Oh, my battery's in. So my PhD students up at the top left have done most of the work. And then my boss in the bottom left, and then various other collaborations who I work with as their statistician to help them analyse some of their neuroimaging studies. So one of the big things about neuroimaging data is it's quite big. But it's not big data. Well, I don't think it's big data, because quite a lot of these studies you have gigabytes of data, but you've only got like 30 people. So, so when you do some of these great reduction techniques, you always have to remember that if there's only like 100 people in your study, you're never really expecting to find something super exciting. Well, I don't think you should. I mean, and so I think that's one of the interesting aspects of in neuroimaging data doing data reduction techniques, is you always have to think about, well, what are you actually doing data reduction on? And how much signal do you really expect to squeeze out of the data you have? So one of the first projects I worked on to try and work with this was basically just doing some lasso regression. You've got these ginormously wide matrices with well, if you're doing it at a voxel level, maybe 4 or 5 million columns and 100 rows. And they want to say, well, what signal can you find? So lasso seems a reasonable way to go about it. As Karen mentioned, I dabble in all statistics, so I thought I'd do this in a Bayesian way, because I fancied trying to learn how to do Bayesian lasso. And it turns out that you can just do Bayesian lasso by putting a Laplace prior on your parameters, which is quite nice. And you get some nice results. So this is a particular study where I was trying to investigate a particular neuroimaging hypothesis. It's called the compensation hypothesis. And the idea that as you age, your brain starts to basically not work as well, but there's this theory that other bits of your brain compensate. So this is an explanation for cognitive reserve. Essentially, as people age, not everyone declines. Some people remain cognitively healthy, and one possible explanation for why that is that some people have this sort of compensation effect. It's a reasonable hypothesis. I tried to put it into a model to see if you could test that hypothesis. The red ones are things that came out significant, and essentially, no. I found no evidence of a compensation effect. But from the mathematical point of view, this slide's the more exciting one, because these are the top. Now, I don't know why, but it's really common in neuroimaging to do a PCA on this ginormous matrix. But quite often they do the PCA, but then keep all the components. So you've taken things that are kind of hard to understand, and now you've made them into some weird transformation, which doesn't really... Oh, never mind. So this is like the top 100 PCA components. There are about 500 in the data. And so there was no compensation hypothesis because the entire left-hand side of the plot, nothing is significant. So if there was a compensation effect, there'd be something on the left and the right, because these are basically two cognitive domains that I'm trying to model and see if there's an effect. But what is nice is that you end up with quite penalized coefficients. So a lot of these coefficients end up essentially on the zero, which is what you want from a lasso effect. So the stats was working, the science didn't pan out in a nice way. Another nice aspect of that one was trying to get them to think about non-straight line relationships. There's a lot, I mean, obviously you only have 30 people or 100 people, so you can't get too fancy with the shape of your curve. But I thought, let's try and think of some sort of, this is sort of like a generalized additive model, or splines effectively. And I did basically try and fit a nice spline to this compensation hypothesis. And you get this nice surface in 2 dimensions then, or in 3 dimensions. And if there was a compensation effect, you would see that as essentially a surface dipping down into one corner, which you kind of see, but it's not significant. So it looks nice, but when you plot this axis back onto the effect of the outcome, it doesn't make a significant change on the scale of the cognitive measures we're looking at. So it was kind of interesting, but again, I wasn't terribly surprised because there's only like 100 people. So it was a lot of work and a lot of interest in getting these very large, wide data sets to run and get them analysed, but not a great success on getting a significant result, which is obviously what you need to get published. Again, I don't know why the whole PCA thing is done, but at the end of it, you can take all the PCA components of that matrix and then put them back into native space for the brain, and you can end up getting nice brain pictures. I like pretty brain pictures. The right bits of the brain are highlighted. If you're interested, I can explain what particular parts are lit up, but essentially the right bits of the cortex are being activated for these cognitive tests, which is quite nice. So that's where I started in neuroimaging, and I thought, that's okay. And then I like this anecdote, it's one of my favourite ones. So I was in a meeting, and the person was doing something called independent component analysis, which is essentially like PCA, but you have a different optimization criteria. And they presented their findings, and they had 14 components. And so I put my hand up on the back. I went, why 14? And they said, with no hint of irony, when you try 15, the code crashes. So I wrote a PhD project and got Matthew to come and try and think about doing an ICA, but in a Bayesian framework, to try and learn the number of components. And it was quite nice, actually. So he worked through some theory to try and represent what is ICA with a variable number of components. Essentially, he went down a lovely way looking at discrete cosine transforms and wave Haar wavelets. So we've gone to the voxel-wise now, so the very, very wide. So if you imagine a brain is basically essentially 60 by 60 by 120. So you've got a large number of columns in your data set. But there's a massive amount of spatial information in there. So how do you try and capture that spatial information when really we believe that there aren't that many useful dimensions? So it's dimension reduction. And he did some really nice work to get this all. So this is all then analysed using variational Bayes. It's all coded up in a language called Julia, which is something you run on clusters. Matthew tells me it works, and I trust him. He's finished now. He passed his Viva in March, so naturally the paper is sat on my desk and I need to get it published, because he didn't get it finished before he left, unfortunately. But the really nice thing is that the method is done on time series data. So, sorry, let's go back. What we got the participants to do, what they did in this study, is they got them to watch a short video called Bang, which is actually an Alfred Hitchcock video. So essentially, it's supposed to induce a sense of fear and anxiety. So what happens is this little boy on the left, he's in his house and he finds a gun and he thinks it's a toy gun, but it's not, it's his dad's gun. And then he runs around the neighborhood playing cowboys and Indians. And right at the end, he points at his friend and goes, bang, and then it cuts to black. So it's supposed to induce an emotional response in the person watching it. We do some weird things to participants when we put them in scanners. But the nice thing is that the analysis that we've got out with these independent components, with all the Bayesian machinery, which obviously we now have a variable number of components, because that's part of our very complex posterior. If you try and then do averaging across components to reconstruct the time series, you get some of these components that then line up very nicely with the red line, which is things happening in the video. So what this video has, it's been annotated with when there's faces, when people are talking, when you should feel anxious. It's got about 30 things that have been annotated for us frame by frame in the video, and you can line those up with the components, the time series components, and see what's reflecting what. And these components then map back to bits of the brain. So there's this one, I think, this one is there's someone speaking, which this then lines up with the audio parts of the brain, the audio cortex. So, it's all really nice. And it was a really nice bit of work to try and do this very large dimension reduction and try and put some principled uncertainty into how many components there are. The other thing you can do with this sort of data, where you have time series, when you don't have an outcome, is sort of resting state data. Does anyone know what resting state data is? So when they essentially stick people in a scanner and say, don't do anything. And they leave them there for 5 to 10 minutes. And then you do that for every participant. And allegedly, resting state data is a good biomarker for various things. So there's a lot of work on resting state data patterns being predictive of various pathologies, like psychosis. I'm not as convinced it's that great for clinical utility, personally, but it's quite interesting. It's vast data sets. You can download lots of resting state data for free of these vast consortiums. But what we're trying to do here is then actually understand between person heterogeneity. Now this is a big area in neuroimaging where traditionally they essentially just take means. So you do sort of means across all your participants and you get an average brain, and you completely throw away the within-person variability. So they have this lovely technique called windowing, where you average all participants' time series and then average over time slices of that averaged time course. Everyone happy with that? It's a bit of a weird thing to do. I don't really know why, because we have multi-level models, which you could then just fit each person as a separate time series and do information sharing that way. So this was a project that my second PhD student, Brio's working on, to try and induce subject-specific levels into these models. So he first worked trying to induce that into this windowing technique, and it doesn't really work. So he built a nice simulation study to try and break the current method. And he said, well, if there is subject-specific heterogeneity, how can that break your current analysis? And so he got a nice paper published, which basically says that the top 3 charts should all be flat, because there shouldn't be any induced correlation effect. But you can induce that by having subjects have subject-level heterogeneity. So one of the major assumptions in the common analysis done in this field is that everyone's the same, so you can just average them together. I mean, it's kind of an obvious piece, but it was quite nice to show it in a graphical form, that essentially this averaging doesn't really work. How am I doing for time? Cool. So the key thing that Brio's now working on, I'll skip the bit in between. So what he's working on now is trying to actually build a hierarchical version of that model. So it's gone into a random graph approach. So they model a lot of brains done on a network level model. So you pretend that the brain is essentially just a network. And so you, again, it's kind of a dimension reduction thing. You take all the voxels and then you put them into regions. You smooth within that region by just taking an average again. And then you assume that that's a node in a network. So what we're trying to do is basically build a hierarchical random graph model, which then there's a whole issue about what summary statistics you use. So you can summarize graphs by a vast number of summary statistics. And the literature is pretty vague on which ones are good. Remembering that the nodes here are bits of the brain, and so the edges don't really exist. That's not how brains work. Scientifically speaking, I'm not really sure what some of these summary statistics mean for a network of a brain, but they're commonly used. So we're just taking that as a given, because what we're interested in is trying to put in a hierarchical framework. And the key thing that kills you there is you have this doubly intractable likelihood. So on the bottom you have this, basically you've got to sum the probability over all of the graph space to normalize the probability distribution. So there's a lot of nice tricks you can do to solve doubly intractable likelihood problems. And that's what we're working on at the moment. And this is the first kind of simulation studies we've got to induce. So we've made up some nice brains which behave nicely. And then we're trying to recover our hierarchical between person heterogeneity. And we get it back reasonably well. You'll have to trust me because it's slightly hidden. So basically the red bar should be the same as the green bars. I think they're reasonably close. So that's quite a nice bit of development. And it's all really just about trying to get into this area, the idea of heterogeneity, and try and stop them just averaging across everyone and getting average effects, because we can do better. That's me done. Thank you very much.
Thank you, Simon, for this overview of neuroimaging.
It's probably a bit quick, but...
Are there any questions? Yeah, it's a topic which is not familiar to myself as well, and especially not based on statistics, but maybe coming from more, let's say, my background. Do you have any issues with multiple testing or trying to you have all these signals, how do you see that there is a true signal? It's not just the many p-values that are below 0.05.
So, so thankfully we've moved away, I say we, the neuromachine field has pretty much moved away from voxel level p-value testing. So obviously rather akin to how early GWAS studies, they realised that, you know, basically if you do a Bonferroni, nothing's ever going to come out. So there was a whole cottage industry of coming up with ways to do voxel-wise testing and then adjust the p-values. We've kind of moved away from that now, which is good. Yeah. Mainly because, I mean, so a voxel at the moment is essentially with a 3 Tesla scanner, it's 2 millimeters by 2 millimeters by 2 millimeters. Inside that box are thousands of neurons. So what we're interested in is what the neurons are doing, but what we're measuring is a vast aggregate. I mean, it's akin in some ways to a spatial statistics, where you essentially observe at an aggregate region level, and you're interested in the point process going on inside, but we've got no way to measure that, because it's at a scale we just can't analyse. So yeah, the multiple testing is a big problem if you start looking at the voxel-wise, and it's even worse, in my opinion, when you go p-value hunting in that direction, and then you look how many rows there are. Yeah, it was very common in the sort of 90s to have big imaging studies would be 30 subjects. And when I say 30 subjects, I mean 30 men between the ages of 19 and 23, who were usually psychology undergraduates. We're doing a lot more population level stuff now. There are some bigger imaging studies. So in the UK, we've got UK Biobank, which is trying to do a big population level representative sample. But yeah, there are still smaller studies kicking around. It's very hard, just to link back sort of in the meta-analysis sense, it's very hard to do meta-analyses at the imaging level because everyone has their favourite way of analysing the imaging data. So if you do your component analysis and I do my component analysis, our components aren't comparable. So how do you do meta-analysis with that kind of data is, well, no one does at the moment.
A question, yes.
This is probably a naive question, I might not understand something you said, but to what extent do the components take into account the, you know, the geography of the voxels?
So with what I was doing with Matthew and our project, we were actually putting spatial priors in. So we could induce some sort of spatial structure, which is an interesting point because our priors were basically built on essentially brain models and brain atlases, basically derived from dissection. So we've chopped up a lot of human brains, so we vaguely know what bits look like on the inside. But to what extent that feeds in, I mean, it was sort of a Bayesian prior thing. So we did fairly weak priors and then put on quite strong priors, which kind of induced the components to essentially semi-replicate existing atlases. And there's a whole spectrum between there. So yeah, I mean, if you read the literature, there's sort of things like the default mode network, which is areas of the brain that people have established as being associated with various cognitive processes.
Yeah, sure. But locally, we're taking into account, you know, X, Y, Z on an individual voxel basis.
Yeah. So
that one thinks to that one, and therefore.
Yeah. So that was in our spatial prior. That was keyed in. So.
And what about in the observation? There's some kind of smoothness. You expect to see some smoothness locally. Yeah.
So there's a lot of. Basically, no one quite knows how to analyse neuroimaging data. So they call it a pipeline. It's what you and I might call cleaning the data. So the big thing also is whenever you see pictures of brains, they all look nice. But actually, from most scanners, they look a bit like Swiss cheese. Because what happens is each voxel, if you're doing a whole time series, you don't usually get every voxel because the coils, you know, they misalign, they misfire. So you have massive amounts of missing data. So in the pre-processing step, before it even gets to me, when they're doing the image reconstruction, they usually have done a spatial smoothing already. And so there's always a slight worry that they might have smoothed out the signal before it even gets to me.
Including some imputation?
It's generally just spatially smoothed on a sort of a nearest neighbour type averaging. They do, they call it 2D smoothing, which I always find funny because it's essentially a 3D object. They smooth in two directions. Again, that's to obey the sort of the brain symmetry. So they smooth from the front to the back and from the top down. They don't smooth sideways across the brain. So you have to stop me. I could talk about brains for a while.
Thank you. If there are any more questions, they can probably
ask
them during dinner.
Oh yes, yes. Happy to talk about brains.
Thank you again, Simon, for your talk.